Welcome back to the next video, everybody. Today we're going to continue looking at Proposition 4 and what I'll call Part 3 in that little mini-series in Chapter 11 here. Today we're going to be looking at reduced Hecke algebras, so let's get into it. We'll let K over Q bar L be a finite field extension with all the associated notation embeddings from the previous few videos, so make sure you're caught up on this chapter before you watch this video, okay? We'll assume L is an odd prime, and we'll fix a representation rho bar from GQ to GL2 of K, which is modular. That is, it's equivalent to rho sub frac m over T sub O mod frac m for some gamma equals gamma sub h of n and some maximal ideal frac m of T sub O, as per notation from the last video. Okay, we'll also assume that rho bar is plausibly modular in the sense of video 11.2, and that sigma is a finite set of primes in what we called sigma of rho bar this chapter. The point of this video is to relate these two notions of Hecke algebras that we've been dealing with together. In particular, we're going to show that T sub sigma, the kind of the sigma Hecke algebra, can be identified with a localization T sub m of T sub O, the full Hecke algebra. Okay, so we're going to do that. First, we need some notation. We'll define n sub sigma to be L to the delta times the product over primes P dividing the conductor n of rho bar, times the product over primes P in sigma minus the prime L of P squared, where delta is 0 if rho bar is good and L isn't in sigma, and delta is 1 otherwise. And then we'll let gamma be the congruent subgroup gamma sub 0 of n sub sigma. Then we'll let F be a new form in cal n sub sigma for this gamma. Recall what that means. That really just means that rho bar F is isomorphic to rho bar over K sub F. So this is kind of the residue field associated to F. This equivalence here happens if and only if A sub P of F, the pth Fourier coefficient of F mod lambda prime, is equivalent to the trace of rho bar of Frobenius at P for all primes P not dividing n sub sigma times L, where what is this lambda prime here? It's a maximal ideal of the ring of integers of K prime sub F, which is kind of the local number, well, not local number field, but it's kind of the QL extension generated by the Fourier coefficients of F. Okay, so under these conditions, we can check that there's a normalized eigenform G in S2 gamma K prime sub F, characterized by the following three properties. If P is a prime that doesn't divide n sub sigma divided by n sub F, the level of F, then A sub P of G is just A sub P of F. We don't change the pth Fourier coefficient in that case. If P isn't L and does divide n sub sigma over n sub F, then A sub P of G is just 0. So we lose all of those Fourier coefficients. And then finally, if we're at L and L divides n sub sigma divided by n sub F, then A sub L of G is just the unit root of x squared minus A sub L of F x plus L. Okay. We will also remark that if L does divide n sigma over nf, then L cannot divide n sub F. And so delta must be 1, as per the previous slide, and rho bar is actually flat. You can see Diamond-Darman-Taylor theorem 3.1f, for example. Hence ordinary, by the very definition of sigma sub rho bar. And so A sub L of F is actually a unit, again, by theorem 3.1f of the Diamond-Darman-Taylor notes. This is just a kind of a helpful remark. Okay. So why does this G exist? Let's modify F prime by prime. So first of all, if P doesn't equal L and it does not divide NF and does divide n sigma over NF, then P is in sigma. And so if we replace F by the new form, no pun intended, P times diamond of PF times P squared Z minus APF times F of PZ plus F of Z, then we have our G. That guy has the desired property at P from the last slide. If P doesn't equal L and divides NF and n sigma over NF, replace F simply by F of Z minus APF times F of PZ. So it's a simpler modification in this case, right? To see that we're done in these cases, these two cases here, it's fastest to look at the L functions of the associated new forms that we just built. For example, the L function of the first modified new form up here is P psi sub F, which is the character of F of P over P to the 2s, minus A sub P of F over P to the s plus 1 times LF of S, which is really just the L function of F with the factor at P removed, which is what we wanted, okay? By the way, the reason we need two different changes here in these two different cases is very simply because if P doesn't divide NF, then the L factor at P is just different, okay? Okay, so what happens if P is L? If P equals L and does divide n sigma over nf, then L cannot divide nf. We know that f has two eigenvalues at L then, call them mu and lambda, with product L times some root of unity, and some a sub L of f, an L-adic unit, by that last fact above that we just got done talking about. And this is also kind of just generally speaking by the basic properties of Galois representations attached to new forms. And that's what Theorem 3.1 in DDT is about, but we've also talked about that a lot in this playlist already, so I won't rehash all this. If, say, lambda is an L-adic unit, just replace f by f of z minus mu f of Lz, and you've got the desired property at P. And so in all cases, we were able to replace f by a cusp form G that had all three properties in that list on the last slide. So who cares about this G? Well, let's see. Lemma G bar, I'll call it. Let f and G be as above. Then the reduction G bar is the normalized eigenform in S2 gamma of K prime this time, which is the residue field of K prime sub f, characterized by the following two properties. A sub P of G bar is trace of rho bar restricted to inertia at P of frob P if P is L, or if P isn't in sigma. And A sub P of G bar is actually 0 any other time. Moreover, if K is as in the previous video, so go check that video, then G is actually the unique normalized new form in SKF, again, notation from the previous video, with this reduction, okay? And I'm not gonna, the proof of this, it just follows quickly from Theorems 3.1 and, for example, DDT, and also Theorem 1.27 there, which is, so Theorem 3.1 there, again, is the basic properties of rho sub f, and Theorem 1.27 there is the basic properties of Fourier coefficients of new forms. We've covered all of this before already in this playlist. I'm not going to get into the detailed proof of this, right? It's not hard at all. And so I think we're set up for the main result of the video then, which is as follows. The thing that we just saw, like one consequence of the thing we just saw, I should say, is that G bar has coefficients in K, and is independent of the choice of f and cal n sub sigma. That's crucial. So this G kind of, it doesn't matter which f we took to begin with. So let's let frac M denote the corresponding maximal ideal of T sub L. Remember, every one of these new forms G corresponds to a maximal ideal of the full Hecke algebra T sub L. You can see the previous video for discussion on that. Okay, here's the main result of the video. We'll call it proposition T sub M. There exists an isomorphism T sub sigma with T sub M. This is an isomorphism of O algebras. And as a matter of fact, TP gets sent to TP for all primes P that don't divide n sub sigma times L. So let's prove this. First, by the properties of the universal modular deformation, if we replace our field K by a larger field K prime, then how does T sub sigma change? If you tensor it up to O prime, you just get T prime sub sigma. And the same thing is true for T sub M. If you tensor T sub M up to O prime, you get T sub M prime. And the latter is true here because there's actually a unique maximal ideal M prime of T sub O prime over M, okay? Who cares? Well, all this is really to say that we can actually assume that K is as in lemma TK from the previous video. It's large enough, okay? Because we can kind of control how these Hecke algebras are changing as we grow the field. We can also note the following. Cal n sub sigma is the set of new forms f in n sub gamma, such that a sub p of f bar, the reduction of f, is trace of rho bar of Frobenius at p for all primes p not dividing n sub sigma L. Okay, what does f bar here mean, by the way? Reduction what? It's f mod lambda. Okay, so what we're going to do first is we're going to define an isomorphism of K algebras called kappa from T sub M tensored up to K, with the product overall f in cal n sub sigma of K. Now, K here in this case is really just K prime sub f. Keep that in mind, okay? And this isomorphism is going to have the following properties. For every f in cal n sub sigma, kappa of T sub P sub f, so kind of this like sequence indexed by these f's of all of the Hecke operators T sub P, what happens if you take kappa of that? You're going to get A sub P of f if P isn't in sigma. What happens if P is in sigma but isn't L? If you do kappa of T sub P of f, you're going to get 0, actually. And what happens if L is in sigma, which is the last case? What is kappa of T sub L sub f? It's the unit root of x squared minus A sub L of f x plus psi sub f of L times L. Okay, so let's do this. Let's recall one thing we already know. T sub M tensored up to K is isomorphic to the product over primes frac P of T sub frac P, where P runs over the primes of T sub K with pre-image in frac M. So by lemma t sub k from the previous video, which is one of the main results there, t sub, that should be frac m, tensored up to k, is isomorphic to the product over f and cal n sub sigma times the product over frac p and what I'll call cal m sub f of a sub kf mod I sub kf localized at frac p, where this cal m sub f here is the set of prime ideals here in this quotient whose pre-image in t sub o is contained in frac m, okay? If f isn't in cal n sub sigma, by the way, then cal m sub f is empty. Otherwise, what does it consist of? It consists of the kernel frac p sub f of the map UPF that maps to a sub p of g, where g is as above, and these UPFs were defined, I believe, last video. Okay. The maps UPF to APG induce isomorphisms between a sub kf mod I sub kf localized at frac p with k, and taking the product over all f and cal n sub sigma gives the desired isomorphism. So in essence, this first stage of the proof of proposition Tm that we're proving right now really just follows from lemma tk from the previous video. That's all it is, okay? Now, if we identify T sub sigma with the O subalgebra of the product over all f and cal n sub sigma of k generated by the Hecke operators T sub p, thought of as like sequences A sub pf running over f, for p naught dividing n sub sigma times L, then to finish the proof of the proposition, we really only need to show, and I'll let you check this, that T sub sigma contains the kappa of Tp for all primes p dividing n of rho bar times L. Now, for each f and cal n sub sigma, rho f is isomorphic to the following composite, the map from GQ to GL2 of T sub sigma to GL2 of k, gotten by composing the universal type sigma modular deformation with the projection from T sigma to k under this identification up here. Okay. Hence, for primes p dividing n of rho bar times L to the delta, where delta was defined in this video, the image of rho mod sub sigma restricted to inertia at p of Frobenius at p and k is actually just rho sub f restricted to I sub p of Frobenius at p, but we already know what that is. That's A sub p of f. Okay. That just tells me, though, that rho mod sigma restricted to IP of Frobenius at p is kappa of Tp, though. Okay. If delta is 0, then lemma TR from the previous video then tells me that T sub sigma contains kappa of T sub L, and so that takes care of the prime L, and we are all set. That proves this thing right here that we needed to show, which gives me the rest of the entire proposition given the isomorphism we just found. Okay, so we're going to keep pressing on towards finishing proposition 4, which is one of the, I think actually 4 major propositions needed for the proof of R equals T in the general case. We'll start doing that next video, and I'll see you then, and thanks for watching.